Welcome back. Our last video for Chapter 5 is going to relate to what we previewed just a little bit ago, and that is applying nested loops to do an image filter. And in particular, we're going to do an edge detection filter. So, the example from the text that does this does an image filter that's an edge detection filter. And a filter to an image, in this case, means looking at all the pixels in an original image, making some change to each pixel, thus creating a new image. So we're going to use nested loops to do that. We'll go through each pixel in the image. Our outside loop will pick a particular row of pixels. The inside loop will then visit each pixel in the row, and then we'll apply our filter to that pixel to produce a new pixel for a new image. And we're doing what's called edge detection. So here's the image from the text example. In this particular case, obviously it's color, whereas the one in the textbook is black and white. But the idea is the same. Here's our nice picture, and when we apply an edge detection filter, it looks like some sort of pen and ink drawing after that's complete. So what's happening is we're going through the image looking for the places where the color changes significantly between two pixels, and that will indicate an edge, which will then be marked as black. When the color is within some threshold being the same, then we'll set the new pixel to white. Okay? So let's look a little more in depth at this. Here's another image. This one happens to be of the engine of a World War II vintage bomber aircraft. So this is the before picture. This is the after picture, after we've applied the edge filter. And now what we're going to do is consider a sub-area of this image. So this red square, we'll zoom in on that in a moment. So this is the before image and the after image, the same area that we'll be looking at. And now let's blow that up. Here's our area in the original image. These are the pixels magnified and drawn on the screen. Okay? What we're going to do is look at two pixels that are right on top of each other. So in other words, if I'm filtering this pixel right here where the pointer is at, then I'm going to look at the pixel directly underneath it and compare their colors somehow. And if their colors don't differ by very much, then in the new image that pixel will be white. On the other hand, over here, if I look at this pixel and this pixel, so I'm filtering here, I look at the one below it, there's a significant difference in their color, and so the new pixel in the image will be black. Okay? And here's how that looks afterwards. So all these pixels that are set to white are ones that were in the previous image. There wasn't much difference, and now in the new image that pixel is set to white. On the other hand, ones where it's black, there was a difference between the pixel above and the one below, so we set it to black. Okay? So here's our procedure. For every pixel in the image, we're going to get the color of that pixel and the one directly below it. Then we're somehow going to compute the average color of each of those pixels by looking at the red, green, and blue components of each. And then we'll take a difference between those averages. And if that difference exceeds some threshold, then the pixel in the new image will be black. Otherwise, the pixel in the new image will be white. Now, one thing we'll have to look at that will change our loops slightly from what we showed in the last video, and that is our Y loop, the one that's looking at the rows of pixels. We'll have to stop one row shy of the last row in the image. So if we go back to our airplane image, here's the picture, and here's the filtered version. If you look at the very bottom, that last row of pixels hasn't been changed. And the reason is because if I'm looking at, say, these are the last pixels in my image, last row, there aren't any pixels underneath, so I can't compare them with anything. So the algorithm, as we're going to present it, just leaves the last row of pixels in the image untouched. All right? So let's move to the whiteboard and talk about how we might solve this problem and how we're going to determine average colors and things like that.
Okay, so here's the idea. We've got an image that's composed of a series of pixels. And we need to look at every row, and then in each row, every pixel. Okay? Perfect for a nested for loop. So our for loop is going to look like this. Our y is obviously the row, because our y dimension in processing runs that way. And if the image we're filtering is called IMG, we're going to go, as long as our y variable is less than, image.height, which would be the height of that image, minus 1, because again, we can't do the last row of pixels. And then increment our y. And then inside that, we'll look at each pixel in the row with our X loop. And that'll just go all the way across, okay? Because we can look at everything in a row. Now what we have to do is get the color of this pixel that's at position XY and the pixel that's right below it. So in the X dimension, it would still be X, but it would be at row Y plus 1. So we're going to save those colors. Call it maybe TC and BC for top color and bottom color. Turns out in processing, there's a method on a p-image object called get, which gets me the color at a particular location. So I'm going to get the color at XY, store it in a color primitive variable called TC, and then get the color of the bottom pixel, XY plus 1, and store it in the place called BC. Okay? Those are two colors. Now to compute their average. Okay? TA for top average. Well, given a color, I can get the red, green, or blue components of that color with the red, green, and blue methods. So red of TC plus green of TC plus blue of TC divided by 3. Okay? That will compute the average color, some sort of grayscale number, based on the red, green, and blue components of the color TC. Do the same thing for the bottom average, except I would use bottom color in each method call. And then what I'm going to do is compare those two by taking a difference of the averages and see if that's less than some threshold. So if the absolute value of my top average minus the bottom average is less than a threshold value, then I'm going to set the color in my image at position XY to be white. Okay? Otherwise, we'll set the color at that position to be black. Okay? So there's a sketch of how we're going to implement this particular algorithm. What we're going to do now is go back to the computer and finish the implementation and show you some specifics about absolute values, what our threshold might be, and so on. Okay? So, back to the computer.
Okay, now we're back at the computer here. We're going to go ahead and look at implementing this edge detection filter program. And what I've done is taken and typed in the skeleton of the program already so that we don't have to worry too much about the miscellaneous pieces that really aren't that important to what we're trying to get across. So for instance, I already have declared the p-image object where the image will be residing. I've created 3 different constants that we'll use. A threshold constant, and that's what will determine whether or not a pixel is white or black in the new image. And then colors constants for white and black so that we don't have to use the color method repeatedly in our code below. Okay? Alright, in our setup piece, all we have to do is size the output window. So we're going to make the size of the display window the same as the size of the image. And then we're going to go ahead and load the image itself using the load image method call. Okay? And that's really about it for setup. And then our draw method is simpler yet. All it's going to do is draw the image starting at location 0, 0 on the screen. All right? We should be able to run this now and see that we just have colored tulips when we run the program. Okay? Very good. So that works. Now what's left then is to go down into our mouse clicked method, and when the mouse is clicked, we're going to go ahead and apply that image or our edge detection filter to change our image into the pen and ink drawing. Okay? So as we discussed at the whiteboard, we're going to use a nested for loop approach. So our outer for loop will be the while loop, and it will go up to but not including the last row in the image so that we don't have to worry about getting pixels underneath the last image, or the last row rather. Okay? And then inside that we're going to go ahead and do our for X loop. So let's put some comments on these. Okay, so for every row, then inside that what we're going to do is look at each pixel in the row. And we use that another loop, our nested loop for that. And we can go all the way across because we're not relying on any pixels to the left or to the right of the current pixel, just the ones right underneath it. Okay? Now what we're going to do is grab those 2 colors. So TC will be the color of the top pixel, and BC is the color of the bottom pixel, the one right below the top. Okay? So color TC. And this is where we'll use that get method. When you apply the get method to an image, what it does is give you the color of the pixel at that location. So we're going to get the XY pixel color, store it in TC, and then for the bottom color, image.get x, y plus 1. So the color right below it. Okay? Now we're going to find the average of those. And we'll store those averages in float variables called TA and BA. All right, now given a color, I can get the red component of the color with the red method, the green component of the color with the green method, and the blue component of the color with the blue method. So if I add those together, each one is a number between 0 and 255. Get all those, add them together, divide them by 3, and now that's the average value for the color on the top pixel. Okay? Basically, I've sort of converted it into a gray color. Then I could do the same thing for the bottom pixel. And now I have my two averages. Now what's left is to compare those averages, find their difference, and compare that to a threshold. Okay? So if the difference between the averages is under the threshold value, we're going to set the top pixel to white. Otherwise, we'll make the new pixel black. Okay, so it's an if statement. Now we need to know how to do an absolute value. Well, it turns out processing has an absolute value method called ABS. So I'm just going to take the absolute value of the difference between those. And that way I don't have to worry about whether the difference is positive or negative. In any case, if that difference is less than the threshold value, then I'm going to use another method on the image called set, which allows me to set the color of a pixel at a particular location. So I'm going to set the pixel at location XY to be white. Otherwise, if I'm greater than or equal to the threshold, I'm going to set the color at that location to be black. Okay? And that's my if for X, for Y, and the end of the mouse clicked method. Now you may be wondering, excuse me, where the value of that threshold variable came from. And the answer is we just experimented, and during the development of this program found over many runs that a value of 9 turned out to be a pleasing value to have. So if you were going to repeat this, you could change the value of threshold to your liking and see which version you preferred. Okay? So let's see how this one works. Again, we start with our initial image. There's the color image. And when I click the mouse, there we go. Now I've got an edge detection filter applied to my image. There we go. That is the last example for this chapter. What we'll do next then is start learning more about how to design and implement larger programs. So things are going to get more complicated, and I want to figure out how to keep big, complicated programs from becoming unmanageable. And that's the topic of the next chapter. See you then.